All right, let's do another geometry. Gauss's law for a plane of charge. Okay, so I'm going to draw the plane. I'm going to draw it as sort of a cut, a cross-sectional cut, like this, and I'll give it a little bit of thickness just so that you can see it. And this is the plane in cross-section. I'm going to draw sort of a little bit of a visualization of it sort of going off in 3 dimensions. We don't need to go to the visualization lab. You get the idea. This is a plane going back into space. It has a charge density sigma. So sigma coulombs per meter squared. And in a Gauss's law problem, first thing I always ask is, what does the symmetry tell us? So in this case, when you have a plane of charge, the symmetry is actually telling you that the E field points normal to the plane. So if I were to put a coordinate system like this, where I have x and y like that, the plane is in the xy, the plane of charge is in the xy plane, then the E field is going to point in z. And you could say, well, what if you come over here? Now it's no longer symmetric because we have more charges over here than we have over here. But actually, we're not just doing this plane of charge. We're doing an infinite plane of charge. Gauss's law, as we're using it here, only works for an infinite plane of charge. Gauss's law works for anything, but for the way we are doing this calculation, it has to be infinite. Okay? Therefore, since the plane actually goes on forever, it's also true that the lateral components of the field cancel. E is also perpendicular to the field here, and it's also perpendicular to the field here. And if you go under the plane, it's perpendicular, but it's going to be down, assuming that's positive charge, and it's going to be down like that, and it's going to be down like that. So basically, symmetry tells us quite a bit. It says that the plane makes a field pointing away from the plane. Okay? So E will be along the z axis. So now that you know that, you need to pick your Gaussian surface. Okay, so let me erase some of this stuff here. Don't need all these. So you actually have 2 choices for your Gaussian surface, and you want to think in terms of symmetry. What do you want? You want faces on the surface that are either perpendicular to the E field, so that their area vector will be along the E field, or you want faces that are sort of parallel to the E field, so that their area vector will be perpendicular to the E field. That's the 2 main things you want in a Gaussian surface. So one of them would be this. Here is a cylinder with a top. It comes down and it pierces the plane there, and it keeps going, and it kind of looks like that. And if we could see through the cylinder, the bottom would look like that. So that's a Gaussian cylinder. And that is one good choice for a plane. But you'll also see this. You'll see what's called a Gaussian pillbox. Now, pillbox is sort of this thing that sometimes a silly word just sticks in physics, and we use it over, and every book uses it, and everybody uses it. And I'm worried some of you might not know what a pillbox is, especially because you're young and you don't need a pillbox yet. Well, I have a pillbox. So this is my pillbox. I got it in San Antonio at the Alamo, and it really is literally, it just means a box. In physics, pillbox just means a rectangular prism. It's just something with 6 sides and right angles on it. That's all it is. This pillbox is important to me because it helps me remember to take my meds, and it helps me remember the Alamo. It sort of does both of those in one thing. So all a pillbox is a little teeny box. Okay? So here we're going to draw a Gaussian pillbox that looks like this, like that, and it comes down like that, pierces the plane, keeps coming down like that. And we could draw the back surface like that if we wanted to, and it would go up. So it's basically just sort of a cube sitting in the surface. Okay? So either one will work. And we're going to do the integral, and it won't actually even matter which Gaussian surface we're using. Okay? So let's see. Gauss's law. Integral of E dot dA is the charge enclosed over epsilon naught. I'm going to write that so many times to make sure you memorize Gauss's law. So when we have the integral around a closed surface, the way we do the integral is we break it up into the individual surfaces. Right? So each one of these actually has sort of 3 kinds of surfaces. They have a top that has its area vector in one direction, they have a bottom that has it in the opposite direction, and they have sides, which in terms of Gauss's law are actually equivalent, because the sides all have area vectors that point perpendicular to the E field. So we could actually just say this is the E field of E dot dA of the top plus the integral of E dot dA of the sides plus the integral of E dot dA of the bottom equals the charge enclosed over epsilon naught. Okay? And then you just look at it and you figure out what those are. And since we've set it up with symmetry, it's not too bad. We could say these surfaces have a top area A, like that. And that's actually all we need to know. We don't even actually care what the length is. You'll see it doesn't matter. So the flux to the top, well, E is up, and the A vector, if we drew it as a vector, is also up. So the angle between them is 0. The dot product is gone. It's just E times dA. E is also constant. If you move around on this surface, E doesn't change as you move around above a plane. It might change if you move away from the plane. We'll see. But moving laterally makes no difference whatsoever. So in that case, this integral just becomes E times the integral of dA. Well, the integral of dA is just that area. So this one just becomes EA. So that's a case where we use symmetry to set up the integral to make it easier. The sides always have their A perpendicular to the E field. Right? Here it comes out, here it comes this way. Therefore, the dot products all give you 0. Right? So the sides don't contribute. The bottom surface has its A going down like that, because remember the area vector always points to the outside. Here the area vector points down. But the E field also points down. If we think about symmetry, here the E field points up, on this side the E field would point down, so it's actually EA again. It's positive flux again. Okay? So there's the integral side of the equation. The other side is the charge enclosed. The charge enclosed is that area times the charge density, right? Because the actual piece here that's enclosed looks like that. It's just, in this case, it's a circle with area A. In this case, I didn't leave myself a lot of room to draw it, but it's a square with area A. So it's just sigma times A over epsilon naught. Okay? So EA plus EA is 2EA, and if you want to, and then the A's cancel, right? So in the end, what you get is that the electric field is sigma over 2 epsilon naught. And if you want to think of it in terms of a vector, you could add a vector, and over the top, it would be in the z direction, and underneath, it would be in the negative z direction. You can't actually write one expression for it, because it's not always pointing the same way. It kind of depends on what side you're on. But here we've solved for the magnitude of the electric field. It's the electric field magnitude is sigma over 2 epsilon naught, and the direction depends on what side of the plane you're on. What's interesting about that is that it doesn't depend on how high you are above the plane. So notice we didn't put a length in there. We could have put an L for the height of that thing or an L for the height of that thing. It wouldn't matter. We never needed it. Right? We never did anything. No part of the integrals needed that L. The only part that involved L, the integral was 0. So what that tells you is the E field is constant everywhere above the plane. No matter how far you go away, it's the same E field. No matter how close you get, it's the same E field. When we talk about, in other parts of the class, here's just a uniform E field, you might think, how did they make that? Well, you could make it with just a uniformly infinitely charged plane. Okay? So I see that we do have a question here. Let's see. Andrea Plan B, why isn't the field infinite on the surface? Why is it? Oh, okay, yes, I've seen this question before. I can tell you why. Very good question. It comes up a lot and actually illustrates almost perfectly a very important point. Let me erase the integrals and draw a little bit more. Okay. So what Andrea Plan B is asking is basically this. Here we have the plane and it's charged. Okay, we're looking in cross section again. And I'm telling you that the E field has a value there, it has a value there, and it has the same value here. And even if you go down within just 1/100th of a nanometer to the surface, it's still got the same value. which seems strange because there's charge here. And when we think about Coulomb's law, when you get really close to charge, the field's supposed to get really big, right? For a point charge, it goes to infinity. So how is it that we can get so close to charge and never actually have a large E field? Okay? And the answer is that our model doesn't let us get close to a charge. This is a limitation of our model. Remember before when I said when you make a model, it's never always accurate, okay? So if I were actually going close to a real object that was essentially a plane of charge, and I eventually got close enough, I would see individual electrons. And if I got close to one of those individual electrons, the field would get really big, okay? So here, this is reality, is individual electrons. In the model, there are no electrons. The charge is smooth. So if I get really close, say this distance is 10 to the minus 5,274 meters. That's really close, okay? If I get really close, the charge that's really having the biggest influence is sort of this charge here and sort of this little cone, this little area right below the point I'm asking about. All the rest basically gives you lateral components that cancel. The charge that really creates this field sticking up shrinks to a ridiculously small value, okay? The amount of charge here is basically sigma times that area right there. That goes to 0 as this separation goes to 0. And since they both go to 0 together, the field stays constant. The field never blows up because you get closer and closer, there's essentially no charge underneath you. The field doesn't go to 0 because as you get closer and closer, you're closer and closer. Okay? So it does actually jive with Coulomb's law. If you remember that you're doing a model, you're not really doing reality. So that's a good question, and that's why you got to keep an eye on your models. Now I must offer up 2 confessions to the spirit of Charles Augustin Coulomb. I've actually been doing 2 things with his law that are a little not so good, okay? So what I've been doing all this time is drawing something like this, putting a plus Q on it, and saying we're going to use Coulomb's law to get the electric field. 2 things, a little questionable about that. One is that you don't use Coulomb's law to get the electric field, right? We know what is Coulomb's law? It is the force between 2 charges. It's not the electric field between 2 charges, it's the force. However, since we basically define the electric field in terms of the force, since it's basically this force F and you just divide it by the Q, to me it's kind of the same thing. So I like to say we're using Coulomb's law to get the electric field. That one, I believe, is forgivable, although maybe I'll get a lot of hate mail about that as we go in the semester. I don't know because it's only July. The other one is that I draw this. I often draw this sort of round thing and put a Q on it, and we calculate or we apply Coulomb's law. When Coulomb's law actually only applies to point particles, it doesn't apply to a big chunk of charge. I've been implying chunks of charge. I think I even said chunk of charge a few times. Coulomb's law really means a point particle, and the point particle we usually think of as at the origin, and we move different radii away from the particle. Here, this has a big radius to it already, and we move even further away. So is that okay? So that's what we're going to find out now when we do Gauss's law for a sphere of charge. Okay? What I've been drawing is basically little spheres, solid spheres of charge. I'm going to draw it a little bit bigger so that, it'll look better when we do Gauss's law. So here, now, let's say we have a sphere. It comes around and goes back like that, and its origin is there, and it has a radius A, okay? And it has a total charge plus Q. When you work on these things, you have to decide, when you're doing solid charges with rho, when you're doing a solid charge density, you have to decide if you're going to think about it as a volume and a total charge Q, or if you're going to think of the charge density. They're really basically the same. So you can either say this thing is Q, and its volume is what? Its volume is the volume of a sphere, 4/3 pi, in this case the radius is A, cubed. Or you can work in terms of the charge density. So here in the problem, I'm telling you that the charge Q is uniformly distributed throughout this entire volume. Therefore, you can define rho. That's a bad rho. Rho is what? Well, it's just Q over 4/3 pi A cubed. So you'll see later how you can do it either way. You can think about either one when you do Gauss's law, whichever one makes you happier. Okay? So now the problem is set up. Solid sphere of charge Q, radius A. We have all these parameters here. First thing in a Gauss's law problem is symmetry. What is the symmetry telling us about this problem? Well, if you pick a point anywhere, say here, the electric field can only be along one axis. It has to be along the axis between the center of the sphere and the point. The E field can only be this way or this way. Okay? And it's a standard symmetry argument. If there were some charge over here creating a field with this component, there would be some charge down here creating a field with that component. All those components would cancel, and there would be no field in the lateral direction. It has to be this way or that way. The other symmetry argument is it can't be this way or this way because neither one is special. Right? There's nothing special about that way. It looks the same no matter how you go around this axis. Therefore, the E field has to be 0. So basically, in this case, symmetry says that E is always radial, or is always points in the radial direction away from the center. Okay? So that's all we need to know. So now we're going to use Gauss's law to figure out what is the electric field. In this case, we have two special regions. Since we have a volume charge density, we can be inside the charge or we can be outside the charge. And we want to sort of solve those separately because they're different places and the Gauss's law application will come out different. So let's do this. Let's do, let's separate that off there. And let's do R is less than A. So that's the region of space where the radius starts here, the origin is 0, and it gets bigger and bigger. As long as radius is smaller than A, it's up to here. So that's basically inside the sphere. So inside. All right, so let's apply Gauss's law. Integral of E dot dA equals Q enclosed over epsilon naught. All right, let's see. Well, what we would want to do is I'm going to clean up my diagram a little bit here to make it clear. And we want to pick our Gaussian surface. And we've already decided that we have spherical symmetry. So as you can imagine, we want to pick a spherical Gaussian surface. Okay, so I'm going to draw just another sphere inside the big sphere like that. And it's also our Gaussian surface. Okay, so let's apply E dot dA to that. So due to symmetry, as you go around the integral, everywhere you go, E has to be in the radial direction, and dA, the A has to be in the radial direction. It always points out. E and dA are always in the same direction. So the dot product goes away. Okay. E has to be constant, because as you go around this Gaussian sphere inside the big sphere, there's nothing special. You're always at the same distance from the origin anywhere you go, so E is not going to change. So it's a standard symmetry simplification is you just have a constant E. The integral of dA is just the surface area of a sphere. Right? So the surface area of the sphere is 4 pi, and it's r squared. Because the sphere of charge has a radius a, we're doing a Gaussian surface out to some radius r. So 4 pi r squared. Okay. That's the left side. The right side is the enclosed charge. That's a little trickier here. So we want just the charge inside this sphere, not the part that's on the outside of the Gaussian surface in the entire thing. So, well, the simple way is just to literally say it's rho times the volume. So we could just say it's rho, which is Q over 4/3 pi A cubed times the volume, which is 4/3 pi R cubed. Looks kind of messy, but that's a standard thing to do, right? The rho is the charge divided by the whole volume times the volume of just the Gaussian surface. And the good news is a lot of that cancels. The 4/3 go away. The pi goes away. A lot of it goes away. Okay. And let's see what is left then if we bring this 4 pi under here. In the end, what do we have? We have E is, let's see, so that r cubed and that r squared are going to cancel. And we're going to have Q over 4 pi epsilon naught, and we're going to be left with an R up here and an A cubed down there. So we get that the electric field as you move away is actually increasing. It's linearly increasing in R. Okay? It's 0 at the origin, which it should be. By symmetry, you could argue that the field has to be 0 at the origin. And it just goes up as a linear function until you get to A, where this equation is no longer valid. Right? It only applies up to A because when you go outside of A, if your Gaussian surface gets bigger, then the amount of charge inside is now different. So let's do the outside now. So the outside is R greater than A. All right. All right, so the integral around the closed surface of E dot dA is Q enclosed over epsilon naught. If you're just waking up, that's Gauss's law. So hopefully you've now got that down as Gauss's law. And now we're doing a sphere out here. Right. Sphere, you know, it's centered on the origin. It has a constant radius r, but it's outside. Well, all the arguments are the same. The E field has to be along the radial direction. A has to be along the radial direction because it's a sphere. They're the same direction. The dot product goes away. The E field has to be constant because it's all in the same radius around the sphere. So again, you just get E. And the area of the Gaussian surface, it's at radius r. It's 4 pi r squared. E equals Q enclosed. Well, that's much easier this time because it encloses the entire charge. So it's just plus Q over epsilon naught. So if we solve that for E, we get something that looks familiar. 1 over 4 pi epsilon naught Q over r squared. So this is inside and this is outside, and they're all in the r hat direction, or they're all in a radial direction. And you will see that the spirit of Coulomb will forgive me because as long as you're outside the charge, it does obey Coulomb's law. Right? This is Coulomb's constant, 1 over 4 pi epsilon naught. It's basically Ke Q over r squared. So what that's saying is, as long as you're outside this spherical thing, it acts like all the charge is at a point at the center. So you can always treat a spherical distribution of charge as though it's really a point charge, as long as you're on the outside. It actually does have to be spherical. So in all my little plus Q's, hopefully it looked fairly spherical. If it becomes not spherical, then it behaves a little bit differently. Okay, so that's the sphere.